morning, guys. Today we're going to start our unit on systems of linear equations. Start with solving linear systems by graphing. What is a linear system, though, you might be asking? A linear system is just a group of lines that all have to be taken into consideration at the same time. So we're talking about solving systems of linear equations. What would the solution to a system of linear equations be? And that would be the point that would satisfy all of the lines or all of the equations in that linear system. Graphically speaking, the point that's on all of the lines. That would be the intersection point of those lines. Now, to find the intersection point, we have a few techniques. One is a visual technique, graphing. And the other two are algebraic techniques, substitution and linear combination. The linear combination technique you may have heard called elimination before. I'll use them kind of interchangeably. More times than not, I'll be saying linear combination. So those are the algebraic techniques. Today we're going to focus on solving by graphing. So to solve a linear system by graphing, there's really three steps. Graph the two lines, find the intersection, and by find, just identify where the two lines cross at, and then estimate and check that point of intersection. Estimate's a very good word to use right here because our answer can only be as accurate as our graphs. And so since we're the ones graphing them and we're looking, we don't know for a fact that that's the exact point where they cross. So we've always got to check and make sure the point we think they cross at is the actual point where they're crossing algebraically. So while it may look like a 4, 1 to us, x coordinate of 4, y coordinate of 1, could be a 3.9 for the x coordinate and a 1.1 for the y coordinate. So that's why the check is very, very important. That's why the algebraic techniques are a lot better because they give us that exact value. But the solving by graphing is a good quick tool if you just need a quick estimate of what the solution would be. So now let's look at this example here. We're going to solve by graphing the system 3x plus 2y equals 2 and negative x plus y equals 6. So as you can see the little curly brace here, that tells you that that's your system. Those are the two lines we have to take into consideration at the same time. And going through our steps, first step says graph the two lines. First, we need to get them into a form I can graph. I could graph by intercepts right now, just by identifying x and y intercepts, but I'm going to go through just a quick review over how to get them into slope-intercept form and graph by slope-intercepts. So if I look at my first line, my 3x plus 2y equals 2. I'm going to isolate my variable. So I need to get y by itself. I've got to move everything away from the y. So I'm going to move my 3x to the other side. So first move the term that doesn't have your variable in it. 2y equals negative 3x plus 2. Next, I've got to move the coefficient. Divide whole sides to keep the equation balanced. So y equals negative 3 halves x. 2 over 2 equals 1. So that's going to be our first equation. Y equals negative 3 halves x plus 1. Let's look at the second equation. Negative x plus y equals 6. Move the x term over, and we get y equals x plus 6. So 1y, we're ready to go. That's our second equation. So y equals x plus 6. So that's going to be our new, it's the same system, just rearranged. Graphing the first line, y-intercept is 1, so go to 1 on the y-axis. Slope is negative 3 halves, so I go down 1, 2, 3 from the y-intercept and over to units. Let's go ahead and draw that. Okay. Line 2, y-intercept is 6. 1, 2, 3, 4, 5, 6. Slope is 1, so I can go up 1, over 1. But since my line needs to come back this way to make it intersect, instead of going up 1, over 1, I'm going to go down 1, left 1. I can still go up and over, and it gives me the same line. I'm just going to work back towards my other line since I'm trying to intersect that way anyways. So let's draw you. And step 2 is fine, intersection point. Well, there it is. Intersection point. And estimated. So if we estimated somewhere around in there, so I don't get a great value to work off of. But just kind of remember, you're working off of a graph, and your answer can only be as accurate as your graph. Say that we tried 5. So what if this was -3, 5? All right. After we estimate, we've got to check that point of intersection. So to check, I need to plug this value into both equations. So I'm going to take my 3x plus 2y equals 2 equation. And we want to know, does that really equal 2? So 3 times -3, 2 times 5, and we're still asking, is that equal? So -9 plus 10 is 1. So that didn't equal out. So we know it's not -3, 5. So I don't even have to try it in the other one. But just to show you how it works going through the other one, -x plus y equals 6. So -3 plus 5. And we want to know, does that equal 6? So 3 plus 5 equals 8. Getting ahead of myself. 3, negative makes 3. 3 plus 5 equals 8. So as you can see, this one was a little too small. This one ended up being a little too big. So my graph must be off a little bit. And as you can see, I'm not really consistent with my scale. So graphing's not always the best strategy. Maybe if I tried, I don't know, -2 and 4. Okay, maybe I just drew my line not quite straight enough. Okay, maybe it needed to be sloped down a little bit more. Maybe I went over too far when I went up 1 over 1. So if I tried -2, 4 as my intersection point, maybe it should have been more like that. Okay. If I try -2, 4 as my intersection point, let's see if that'll equal 2. So -2 and 4, and 3 and -2 is -6. 2 and 4 is 8, which gives us 2. 2 equals 2. That checks. -2 and 4. So -x is -2 plus 4 for the y. -2 is 2 plus 4 gives us 6 equals the 6 we needed. So that checks. So -2, 4 ends up being our solution. Again, if you're going to use graphing is great if you just need a quick idea of where that intersection point is going to be, where that solution is, or just rough, ballpark figure for it. If you want precision, you're going to need to use graph paper to have a very, very accurate graph, and you need to be using a straight edge. I had the straight edge, but I didn't have the graph paper, so my graph obviously got way offline because it looked a lot closer to -3, 5 than -2, 4. So that's why it's always important to go in and check and use a precise equipment. Okay, now we have our second example right here. So these are already in slope-intercept form, so we can go about graphing them. So let's set up my coordinate plane. Again, you probably want to be using graph paper, but I don't have my graph board right here. But the process is the same. So first line, slope, y-intercept is 3. Slope is -1, so down 1 over 1. Let's try putting those two lines together. Y-intercept for the second line is -2. Slope is 1 over 1, up 1 over 1. Let's try putting those two together. All right, so it looks like, again, we're not quite on a point. So let's try this one just out in space. Let's try 2.5 over and up a half. Over 2.5, up a half. Let's do the arithmetic and see if it works. So trying the first one, y equals -x plus 3. So y value should be a half. And we want to know, does that equal, my little question mark equals, negative 2.5 plus 3? Well, if I do 3 minus 2.5, do I get 1/2? Yes, I do. So we can see that that checks. Let's try the other one. Y equals x minus 2. So y is going to be 1/2 again. Does that equal 2.5? It's a horrible 2. 2.5 minus 2. Well, 2.5, take away 2, will leave me with 1/2. So that one checks. So that one, despite it looking like it being off, was actually more accurate than the last one. So again, to test the accuracy of your estimate, you always need to check. So that's how we always identify. Is this point a solution? We just plug that point in, x value for x, the y coordinate for y, plug that point back into both equations, and for it to satisfy, for it to be the solution for the system, it has to satisfy and be a point for both equations. So now let's just work on checking a point at a time. Instead of saying solve, they give us a point, they give us a system, and they want to know, is this point a solution to the system? Well, how do I determine if a point is a solution to the system? Same way I determined if the points I estimated were solutions to the system. Plug them in and check. Each point represents an x coordinate and a y coordinate. So the x's get substituted for the x's, the y's get substituted for the y's. We see that it works out. So I'm going to take my 5x minus 3y equals -4 equation, my x plus 2y equals 7 equation. And it's 5 times the x coordinate 1 minus 3 times the y coordinate 3. And I want to know, does that equal 4? Is -4. Is 5 minus 9 equal to -4? And the answer is yes, -4 equals -4. Check. This one, x coordinate, which is 1, plus 2 times the y coordinate, which is 3. Does that equal 7? Yes, 1 plus 6 equals 7. So 7 equals 7. Check. So yes, 1, 3 is a solution to the system. Let's do it again over here. 2x minus 3y equals 6. -4x plus 6y equals 6. And let's test the -1, 2. So 2, -1 minus 3, 2. Does that equal 6? So -2 minus 6, it's actually what, -8? So does -8 equal 6? No. So that point didn't even work in the first one, so we know it's not going to work in the second one. But let's just check just to see. So -4x, so -4, -1, plus 6, 2. And that's going to give me 4 plus 12, which is 16. Does 16 equal 6? No, it doesn't. So it didn't work in either equation. So it's definitely not going to work for the system. So to determine if a point is a solution to the system, it has to be a point on not just one equation, but both equations. Let's actually look at this system right here, because there's something special going on with it that I want us to consider. If I looked at the graph of this system, so I go over to each of these equations and get them into y equals 4. 2x minus 3y equals 6, and -4x plus 6y equals 6. And I want to graph them. I want to find what a solution to this system is, because we know that that didn't work for either one of them. So let's find something that does. So put it into slope-intercept form. -3y equals -2x plus 6. Divide by -3. everything on both sides we divide. So y equals positive 2/3 minus 2. So we'll let that be our first line. Y equals positive 2/3 x minus 2. Second line, move your 4x to the other side. 6y equals 4x plus 6. Move your 6. So divide everything on both sides by the 6. So y is equal to 2/3 x plus 1. There's our second line. Now, if I look at the graph, first line, y-intercept is at -2. Slope is 2/3, so go up. Let's grab the blue marker. Up 1, 2 over 3. Grab my ruler. Next line, go to positive 1. Slope is up 2 over 3. Grab my ruler. Now, if I look at those two lines, right now I don't even see an intersection point. So I can't even see that these are going to intersect, and they look like they might not intersect ever. Okay, now my graph's a little bit off, but something in the setup of the equations can tell me whether or not they'll intersect. So these lines right now appear to be lines that don't touch. What we call lines that don't touch, we call them parallel lines. So right now they look to be parallel. Now, how can I know for a fact that they're going to be parallel? What in the equation tells me that they're parallel, meaning they're going the same direction but will never touch? The slope does. Remember, slope dictates the direction of our line. So they have the same slope, which tells me that they're going to keep going up 2 over 3, up 2 over 3, up 2 over 3. Both of them will forever. They're going the same direction, so they will never, ever, ever touch. So that's a very important thing to see. If I'd have known that right away, I'd have known that this point wouldn't have worked. I would have known that there is no solution to this particular system because there will never be an intersection point for these two. So that's also something else that's important to do, and that's called classify the system. We classify a system one of 3 ways. We say it has one solution. We say it has no solutions. And then the third way, does anybody remember what the third way is called? We say it has infinitely many solutions. Infinitely many solutions. Now, one solution we've been working with. Lines cross one time. Well, what causes a line to cross one time? Just being at a different angle. Because if they're at any different angle, they're going to cross at some point. Even if it's out towards positive or negative infinity, they're going to eventually cross. So the angle of the lines is dictated by the slope. So one solution occurs when the lines have different slopes. No solutions occur when we have parallel lines. There's no times they will ever intersect. So that tells me they're going in the same direction. They have the same slope. But they can't just have the same slope. They've got to have the same slope and have started at different points. So it's same slope with different y-intercepts. Same slope, different y-intercepts. And the last scenario is infinitely many solutions. If they have different slopes, they're turned at some angle and they're going to cross eventually. If they have the same slope, they're going in the same direction, but different y-intercepts puts them in different places. So parallel line. Well, what if they have the same slope and the same y-intercept? So they start in the same place and they're going the same direction. That's two of the same line. So that's your infinitely many solutions. Same slope, same y-intercept. Same y-intercept. So just by identifying these quick things, I can classify a system without actually solving and seeing that it has no solutions. Okay, so here we go. We've got three systems that we want to classify. One solution, no solution, or infinitely many solutions. So we're going to start by looking at the slope. Slope, I don't even have to get into slope-intercept form. Slope is rise over run. We get that from our y's divided by our x's. So let's just look at the ratio of y coefficients to x coefficients. My y is 1, my x is 1. So the slope for the first one would actually be a negative 1 because we'd have to move it to the other side. So the slope for the first one is negative 1 to 1. For the second one, the y is negative 2, the x is negative 2. So what we're looking at is if we move to the other side, we're going to have positive 2 to negative 2. So positive 2 to negative 2. And when you actually simplify that, you get negative 1 and negative 1. Slopes are the same. Now looking at your y-intercepts, divide the 1 over. The y-intercept for the first one is 7. Divide the negative 2 over, because that's how we get it. The slope is, or the y-intercept is going to be negative 2. So on this first one, slopes are the same, but the y-intercepts are different, so we can say that it has no solutions. Same slope, different y-intercepts. Let's look at the second example. Slope for the first one, I'd move my 2 over, so negative 2. I'd divide by negative 4. Negative 4 gives me a half. Second equation, I'd move my 4 over, so negative 4. I divide my negative 2, so I get positive 2. I don't even have to go any further now because I see my slopes are different. So as soon as I have different slopes, we know it's one solution. And then the last line. I'm sure you can guess which one this one's going to be. But let's look at the line. Move my 5 over. Move my 2 over. Slope is negative 5 halves. Here, move my 10 over. Move my 4 over. Remember, we're subtracting the x stuff. We're dividing the y stuff. I get negative 5 halves again. So the slopes are the same. So let's check the y-intercepts. Y coefficient into the constant. So b is 10 over 2, which is 5. Here, the slope, or the y-intercept, y equals mx plus b, is going to be the constant over 4, which is, again, 5. We can see that the y-intercepts are the same. So same slope, same y-intercept, infinitely many solutions. Now, you don't even have to get that far into it. We should be able to look and see if the x's and y's have the same coefficients, or multiples of the same coefficients, then they're going to have the same slope. Right here, I have 1 and 1, and here, they're both a multiple of 1 and 1. They both got multiplied by negative 2. Okay, so these are going to have the same slope. Looking at my y-intercept portion, though, from my constant, this was a 7. Well, if this got multiplied by negative 2, this by negative 2, this would have to be negative 2 to be the same. So since this is not a negative 14, 7 times negative 2 is negative 14, then we know that these are going to be different values. So if the one line is a multiple of the other line, it's the same line. So that tells me that they're on the same slope, but they're going to have different y-intercepts. Where here, 5 to 2, well, I can multiply this by 2 and get 10. This by 2 gives me 4. This by 2 gives me 20. So they're multiples of the exact same line. We call those scalars. Sorry, scalar multiples of the same line. So while this has a certain length, this is 2 times longer. because all the values got multiplied by 2, which, when you're talking about infinity, twice as long as, the same thing. So since everything was a multiple of the same value, every term was, that means that they're the exact same line, just one stretched out twice as far. And then we can see this one here, multiplied by 2, this one divided by 2. As soon as you do that, you know that you have different slopes. So we can do it analytically without digging in and doing the actual calculations. But when all else fails, convert them to slope-intercept form and say different slope, same slope with different y-intercepts, or same slope with same y-intercept. So solving linear equations by graphing, it's not the greatest technique in the world. It's inaccurate sometimes if your tools or your ability to draw graphs are a little bit off, but it gives you a good idea of the types of equations you're looking for, how to quickly check to see if you have a solution. Types of solutions you're looking for, how to check and see if you have a solution, and just get a ballpark figure of where a solution might be. That's solving systems of linear equations, and I will, by graphing, and I will see you in class tomorrow, guys.